Okay, so we are going to do some more problems and calculate AC power in different circuits. As usual, I will ask you questions, make sure you respond back with the best of your ability as how you are going to solve these circuits if you are solving it instead of me. So let's do some circuits. So this is still AC power. Okay, these boxes that I'm showing, they are impedances. So instead of showing them separately, resistors, inductors, and capacitors, I'm just going to put impedance in there. Okay, this is your circuit, 4 impedances, 2 inductive, um, well, 2 inductive impedance and 2 capacitive impedance, and 2 sources, of course. And let's say calculate. So we have to calculate 5 things. Active reactive power Vs1, power factor Vs1, active reactive power of Vs2, power factor of Vs2, and this resistor, this impedance, which is in the common branch between loops 1 and loops 2. Loop 2, if we call this loop 1, call this loop 2, and call this loop 3, then we have to find how much power is consumed in that Z2, active and reactive. When you're writing it, I'm gonna prepare my Octave. Okay, so let me enter all of my numbers and then we are going to discuss the problem. So VS1 is 10 volt, VS2 is 22, and also I'm just going to convert that. Volt rec 22, and C1 is 5 plus J2, 5 plus 2I, Z2 is 6 plus J5, Z3 is 7 minus 6I, and Z4 is 5 minus 5I. Okay. All right, guys. So who is going to help me out now to decide how you're going to approach this problem? You know what we need to find, and to find all these quantities, first you have to decide what you need, and then how you are going to get those quantities. So to calculate the active and reactive power of VS1, what do we need? It's already in rectangular 10. It's the value is 10 because angle 0. Oh, so yeah, so it's 10. Yeah. Yeah. So we need to find the current passing through VS1 to calculate the active and reactive power. And if you know the value of current, of course, the current that you are finding, of course, that's going to be in the phasor form. So once you know the angle of that current, you know the angle of voltage, and you can easily calculate the power factor as well, right? So all you need to do is to find the current passing through VS1, and then you can calculate first and second. Likewise, same thing applied on VS2. We need to find the current passing through VS2 to calculate the active and reactive power, as well as the power factor. The third and the last thing is, fifth thing is power in Z2. So what do we need to do to calculate power in Z2? Yeah, we can, well, we can calculate both voltage and current, or at least we need the current. Because if you do have the current, then you can calculate the active power, because 6 is the resistance and 5 is the reactance. So if you know the current, of course, current passing through the impedance will be the same, and we can calculate the active and reactive power. So you need at least the current. If you have the voltage, that's fine. You can have both voltage and current. One thing, be very careful. If you just find the voltage, you cannot use V square over R and V square over X. Why? Because that voltage that you are trying to find, that's going to be across the whole impedance. It's not going to be across the resistor or across the reactance. Remember, V square over R, to to use that formula, you need that V across R to calculate the active power, and then the V across X to calculate the reactive power. If you use V square over R or V square over X. In this case, if you find V, let's say you find V at the node, which will be the V across Z2. If you find that V, because many students make that mistake when they're calculating the voltage across an impedance, they calculate the complete voltage across the impedance, but they use the same voltage to calculate the active and reactive power using V square formula. But remember that formula, that voltage is across both components. It's not across the individual. So if you either you find the voltage across individual by voltage division, or find the current, because the current is passing through both components. It's the same current passing through both. Then you can use I square times R and I square times XL, because current is same. So do not make this mistake. This is a very, very common mistake, that student find voltage across impedance and use that voltage to calculate power using V square. But you cannot do that, because that V is not across individual component. That V is across the impedance, whole impedance. But if you find voltage and current both, then you can apply V times I times cosine theta minus V and V times S times sine theta minus V to calculate active and reactive power. So that is still valid. But you need to have both voltage and current in that case. So just have to be careful with the V square over R formula. That for that you need V across R and V across J5 in this case. Okay, so let's do the first one. So to do the first one, let's see what do we know and what do we, how can we find the current at VS1? Oh, and look at it in a broad way. What you should do to find the current in VS1, and you need to know either the voltage or current in Z2. Say it again. Okay, so you guys are jumping in the mesh analysis, and there are three loops, three meshes. Okay, it's fine, you can do it. And it's not difficult, because of course, if you're using MATLAB and you're creating matrices, it's very easy to solve using MATLAB. So, but there are three meshes, that means three equations. Now, if I tell you, of course, you know the voltage at this node. And again, you guys jump into mesh as soon as you see it. Node A, you know the voltage at node A. What is the voltage at node A? VS1. You know the voltage at node B, which is VS2. The only node that you do not know the voltage is node, let's say, C. So if you only apply nodal analysis at C and find that voltage, then you can find the current in Z2. You can find the current in Z1. You can find the current in Z3. And of course, you can apply KCL to find how much current is passing through VS1, because VS1 current is going to be what? The current going into Z1 or coming out of Z1, whatever, based on your direction, and the current in Z3. Those two current, when you add them, subtract them based on their direction, that will make the current of VS1. And likewise, the current passing through Z4 and then passing through Z3, those two current will make up the current passing through VS2. And if you find the voltage at VC, you know the voltage across Z2, you can calculate the current across Z2 using Ohm's law. And then you can easily calculate the power dissipated in Z2. So I wouldn't touch mesh analysis. I will do nodal analysis, apply it to find the voltage at C, and that will be perhaps the easiest way to solve this problem. Not that mesh is hard way. I mean, you have only three meshes. So it's like you write three equations, you use MATLAB to solve those three equations. It's still easy. But I'm assuming that just finding the voltage at node C and then using Ohm's law to find everything else might be much easier. So let's do that. So as soon as you look at nodes, I mean meshes, do not jump directly into mesh analysis. See if you know the node voltages and stuff, and we discussed that several times. I forgot one thing. I have to create multiple pages. Let's see, insert a blank page, and then let's take all this, Control C, put it on page 1. Control. make multiple pages. So once again, guys, learn the lesson. Mesh analysis is everyone is tempted to use mesh analysis as soon as you see loops, but it's not always wise to do that, and that has been discussed over and over and over again. So let's go ahead and apply KCL at node C. Let's assign some currents. Let's say the current here is IS1, the current here is IS2, this is I2, this is I1, this is I4, and let's assume that this is I3. And again, the directions are shown, so we're going to use those directions when we are writing equations for KCL as well as Ohm's law. Remember, it all depends on the direction of current that you're choosing. Your answer should be according to the direction that you choose, and you should write your equations according to the directions. So when we apply KCL at node C, what will be the equation for KCL at node C? Who is going to tell me? I1 plus I4 going towards I2 going away. So I1 plus I4 equals I2. I1 plus I4 equals I2. Okay, I1 in terms of Ohm's law is what? Yeah, VA minus VC, or VS1 is VA. So VS1 minus VC over Z1. VS1 minus VC over Z1. What about I4? VS2 minus VC over Z4. VS2 minus VC over Z4. And finally, you have the current I2, which we are trying to find actually. I2 is VC over Z2, or VC minus 0 over Z2, but you don't have to write 0, but VC over Z2. Okay. So now let's calculate VC. So VC, I'm going to take these two VCs on the other side of the equation, becomes positive. And then on the right hand side, on the left hand side, I will have VS1 over Z1 plus VS2 over Z4. And on the right hand side, I will have VC parentheses 1 over Z2 plus 1 over Z1 plus 1 over Z4. So that is going to come and divide the left hand side. So I will have 1 over Z1 plus 1 over Z2 plus 1 over Z4. Let's go ahead and do that. Let me do it here so I can see the equation. And you guys do it as well, because you need, again, if you're doing it, that means you are doing the practice with me and you can catch my mistakes and you can have practice so that you can do it quickly in the exam and the quiz. So I have VS1 over Z1 plus VS2 over Z4 divided by 1 over Z1 plus 1 over Z2 plus 1 over Z4. 6.99, almost 7. So 7 plus 6.8 plus J 6.82. So 7 plus J 6.82 volt. No need to convert it into polar form, because again, this is not our final answer. This is just a step to find other quantities. Let me know if you're getting the same result. Make sure you do it. Again, I keep asking you guys to do it with me, because if you don't, then you're not going to get practice to do it again during exam, and observe how I show my work. This is what I'm expecting from you. I'm not expecting from you to plug in the number every step and then calculate it and show me. No, I'm just expecting you to write the equations that I'm writing, calculate the result properly, and then show your final result. So this is my VC, and I can see that you are using the correct variables and everything. Yes, Rudy. Yeah. Rudy, you're good. Should I scroll down or you're copying it? Okay, go ahead and do it. You got it? Okay, good. You got it as well? Got it? Okay, good. Okay, so Lazaro got it, and Yunus got the same result. We're gonna move on. So we know VC now. We can actually, since we know VC, we can find different currents, and then that's all we need. We need to find the current IS1, current I2, and current IS2, and we can calculate everything. So let's go ahead and find I2 first. Therefore, I2 can be calculated as VC over Z2. So I2 is equal to VC over Z2, 1.247, so 1.25, plus 0.098, so plus 0.1, I would call it, plus J 0.1, 0.098, so I'm going to round it up to 0.1. That's ampere. Of course, in MATLAB, I'll keep the same values. So I'm just rounding them off right now. So this is my I2, and when I have my I2 and I have my VC, I can calculate number 5 first, let's say. Number 5 is active and reactive power in Z2. So active power in Z2, P, Z2 is magnitude of VC, magnitude of I2, cosine, angle of VC minus angle of I2. But since we know the current, we can also use I square R and I square X, whichever way you want. Perhaps that might be easier. So if we calculate this and write it down in terms of polar form, let's write this down. So magnitude of I2 and phase of I2 is equal to rect pole I2. 1.25. This is 1.25 angle, 4.5 degrees. Yes. Circuit. So either we can use this equation, magnitude of VC times magnitude of I2, assuming both sources are given. Let's actually mention it. Let's assume these values are RMS, so that we don't have to convert into RMS. If they're not given in RMS, assume their peak and then convert into RMS. But let's assume they're RMS. Yes.
So that's in the beginning when you had first asked the first question about what that's why I was thinking to go from 10 to whatever.
That's fine. That's fine. If you assume to be peak, if you're assuming both voltage to be peak, and if it is not given, actually, if it is not given, assume them to be peak. And if it is given that they are RMS, then use RMS. If it is given in time domain, then it's always peak, right? But if it is given in phasor domain, then sometimes phasor domain you can give RMS value or you can give peak value. Mostly you give peak value. But if you can, if in some book they say take it as RMS, the magnitude take RMS. So in that case, let's assume we are taking RMS in this case. So 10 is RMS. Peak will be 10 times the square root of 2. Yes, yes. If it is not being told, assume every time it's peak and then calculate RMS. Yeah. In time domain, it's always peak, remember, because time domain signal is going to be 10 cosine omega t plus theta, right? So the 10, of course, is represent the peak value of cosine, always. Okay, so either we can use this equation, as I said, or simply we can use the magnitude of I2 square, and since it's already RMS value, square times resistance 2, and reactive power of Z2 is going to be magnitude of I2 square times the magnitude of the reactance. So whichever formula you want to use again, but make sure you use it correctly. As we discussed, the voltage, do not fall for the voltage, do not use V square unless you calculate voltage across each component separately, because this VC is the voltage across the total impedance R plus XL. Yes. Well, beneficial in what sense you're talking about? Because right now you do need the voltage in order to calculate each current, so you can calculate the current through the sources, right? So, and then again, if you don't want to use I square R, that's perfectly fine. Since you have the voltage value and you have the current value, then you can still use the basic formula VC I2 cosine of this and VC I2 sine of this to calculate active and reactive power. It's the same thing. In this case, you have to find voltage anyways, because you need to find different currents in order to find the total current passing through each source. For that, you need voltage, right? But if I'm calculating it, and if I can just find the current passing through an impedance, if I have to calculate the power, then I will not find the voltage, I will find the current. Because if I find the voltage, then again, that voltage is going to be across the complete impedance, not across each individual component. Yeah. So let's go ahead and calculate these. So PZ2 is magnitude of I2 square times real of Z2, and QZ2 is this. Okay. So again, when I'm using MATLAB and Z2 is defined as a complex number, all I have to do is to extract the real part, I just use the real function, and extract the imaginary part, I use the imaginary function. So I don't have to rewrite the equation, I just recall the equation, change some variable, PZ2 change to QZ2, and real change to imaginary. So I don't really have to keep typing the same thing. And again, that's a good thing with MATLAB or Octave, that you can recall the equation and modify it quickly in order to calculate the next quantity. It doesn't take much time. And I'm going to post that code, of course, as usual. So this quantity is coming out to be 9.3889. So let's say 9.39 watt. And this quantity is coming out to be 7.82 volt ampere reactive. So this is one set of answers for part 5. So we did part 5 first. See if you're getting the same result. You got it? Okay. Yeah, that was the last one. Active and reactive power of Z2. Since we had the voltage and current, so I just calculated the last one first, because to calculate the current passing through VS1, we still have to calculate this current, and then to calculate this current, we have to calculate I4. So we have to calculate now I1, I4, and I3 in order to calculate the currents of VS1 and VS2. So let's go ahead and calculate I1 and I3 to calculate IS1. So what if I apply KCL at node A? What is going to be my result? No. KCL. Okay, so IS1, since we need to know IS1, so IS1 is equal to I1 minus I3. because IS1 plus I3 is I1. So IS1 is equal to I1 minus I3. To calculate the current IS1, apply KCL at node IS1 is equal to I1 minus I3. Okay, and I1 is VS1 minus VC over Z1, and I3 I'm assuming is VS2 minus VS1 over Z3. Let's see. So VB minus VA, which is VS2 minus VS1 divided by Z3. That's I3. VS1 minus VS2 divided by Z3. So let's calculate that. IS1 equals VS1 minus VC divided by Z1 minus VS1. Actually, that's VS2 minus VS1 because the direction of IS3 is in the opposite direction. So this is VS2 and this is VS1. VS2 minus VS2 minus VS1 divided by Z3. And that comes out to be IS1 is negative 0.022, no, 0.22, negative 0.22 minus J, 2.8, 2.8. That's my IS1. So we can calculate 1 and 2 now first, which implies part 1. And we can calculate complex power, because the real part of complex power is going to be the active power and the imaginary part is going to be the reactive power. So instead of calculating them separately, we can calculate just the complex power and look at the real part as the active power and look at the imaginary part as the reactive power. So complex power of VS1 is, calculate, what is the formula? Anybody remember the formula of complex power? Complex power? Yes, but other formula to calculate that? V times the conjugate of current, exactly. So VS1 times IS1 complex conjugate. This is like the easiest way to calculate the complex power if you know the voltage and current. So VS1 equals VS1 times conjugate of IS1. Okay, this is coming out to be negative 2.26. No, don't worry about negative here. Negative sign just tells you that the current we assume is in the opposite direction, because again, the active power cannot be negative, remember, right? Plus J 27.96 volt. So the active power of S1 is 2.26, or you can also assume that the source is being charged. It's not supplying the power, it is consuming the power. The power is coming into the source. So it is taking the power instead of giving up the power. I'm sorry, CONJ in MATLAB, yeah. So I did not did it specifically, but it's going to be negative 0.2265 plus J 2.79. Imaginary part, yeah. Okay. Any question about this, guys? Anything before we move on? Again, all the power formulas, power factor, make sure you have them in front of you on a piece of paper in MATLAB. Create a code so that you can plug in the current and the voltage, and it calculates power factor, everything. It can calculate from simple code, basically, right? So you don't really have to go and then do it manually. Those formulas do not change. Again, either you are doing it in your calculator or in MATLAB. Those formulas are not going to change, right? So I don't mind you have a piece of code. All you have to do is to, again, analyze the circuit and calculate the current value, the correct value of voltage and correct value of current, and then feed those voltage and current in the program, and it's going to spell out everything: active power, reactive power, complex power, power factor, everything. So create that piece of code. Basically, it's going to be very helpful. I should do that as well. I don't have it in front of me, but I should do that as well. Okay. And then the power factor, of course, we can calculate. Number 2, power factor, cosine of the angle of Vs. This is power factor of Vs1. So the source angle, of course, is 0, and the current angle is, where is it? Angle of IS1. Angle of IS1. I did not specifically calculate it, but I can always write down angle of IS1. And that's going to give me, again, a negative power factor. Negative power factor does not exist, remember. So it's the positive power factor, but since the direction is giving me is doing it in the third quadrant, basically, because the values that I took is like all over the place. So the source is being charged and all those things. So I'm going to put down the actual value, negative 0.08. Right, yeah, negative 0.08. And looking at, again, the source is being charged. So looking at the current value, if you take this to be positive and take this to be negative, then the current angle is going to be lagging the voltage angle, because again, this is in the second quadrant. So the angle is more than 90 degrees. The angle should be between 0 and 90 degrees. But the current is in the second quadrant instead of in the first quadrant. So again, the source is being charged. The values that I took are, as I said, they're all over the place. I just chose the random values. But make sure your power factor is never negative. It's positive between 0 and 1, either in the first quadrant or in the second quadrant. So that's going to be 0.08 lagging or leading. So I'm going to write this down. Power factor is not negative. Let me write it here so I don't have to use multiple lines. positive or 0, 0 and 1. The chosen values made the current in VS1 to be in the second quadrant, hence the phase difference between the voltage and the current is in the third quadrant, which is giving the negative power factor. So once again, source is being charged. The current is going into the source, and that's what you see. The active power is being negative instead of positive. That is, instead of giving up by the source, it's consuming the power. And likewise, reactive power is coming from the circuit instead of this power being given by the source. So again, my values are all over the place. Process is correct, and values are correct according to our numbers that we took. But the numbers, again, make sure numbers make sense. This number does not make sense. That's why I gave the whole explanation. Power factor cannot be a negative value. It has to be between 0 and 1, because your difference between the voltage and phase is in the either the first quadrant if it's a inductive load, or in the fourth quadrant if it is the capacitive load. All right, let's move on and do part number 3 now. And to do part number 3, that is to calculate the power VS2. What do we need to do? We need to find the current IS2. And to find the current IS2, we write the KCL equation again. And KCL equation is going to be what? IS2 is equal to I4 plus I3, yes. So IS2 equals I4 plus I3. So this is current S2. Current through VS2. IS2 is equal to what was it? IS3 plus I4. I mean I3 plus I4, right? I3 plus I. Okay, I3 is passing through Z3, I4 is passing through Z4, but what are the voltages? I4 voltage is VS2 minus VC, and I3 voltage is VS2 minus VS1. So VS2 minus VC is I4. VS2 minus VS1 over Z3 minus VS2 minus VC over Z4. Let's calculate that. So again, the third current is coming out to be in the third quadrant. My values are not very good. They're all over the place. Negative 0.92 minus 0.0, I would call it 0.07 ampere, which implies the complex power of source 2 will be the source 2. Yes. Oh, yeah. Why it is minus? I don't know. My bad. It should be plus. Let's go and do plus, and that will make the values positive and different. I don't understand why I put minus. So there's plus right here. Plus right here. So now let me write down the new one. So it's in the first quadrant, 1.47 plus J 2.89, so 2.9 ampere. So let's calculate the complex power. Vs2 conjugate of Is2. So that is S Vs2 is equal to Vs2 times conjugate of Is2. 53.91 minus J 46.90. So 46.9 volt ampere, which means that it is giving 53.91 watt of power. And 46.9, negative 46.9 volt ampere reactive power. Now, reactive power negative means that actually that power is being received or it's coming from the capacitive loads. So that's, and then we can calculate last one, power factor of Vs2, which is cosine of the angle of Vs2 minus angle of Is2. Angle of Vs2 is 22 degrees. 22 times pi by 180. And angle of current is, I can calculate that, angle of Is2. .7544. Not sure lagging or leading. Let me see what is the angle of current. I think, well, the power is negative, so it's going to be a leading power factor. Because the current, the reactive power is negative. Angle of current is 63.02, which is leading the phase of the voltage, which is 22 degrees. So it's a leading power factor. And these are all the values that were required. So first voltage source is being charged, yes, because remember your active power cannot be negative for the source unless you are sending the power back to the source, active power. So let's say you choose you're finding how much power is like DC power, right? You're finding how much, if you have two sources, how much power the source is supplying, and it turns out to be a negative value, that means source is not supplying that power, it is consuming that power. And that's what it shows basically.
And that's the second source.
It is giving up the active power, and the reactive power, the source is looking rest of the circuit as a capacitive load. So it is the power of that source is a negative value basically. Okay, guys. So these are the calculations. These are the values. Let's go ahead and save this thing. Have I? Okay, I have not created. Let's do this here. Week 13. One day. And 03/31/2020. Let me go ahead. Yes. Yeah, give me 1 second. Let me go ahead and copy this real quick. So I'm going to post my MATLAB work as well in case you want to see that. This is the MATLAB work. Go to what? First KCL. Okay. Let's see. This one? Case. I1 plus I4 is equal to I2. Let's go and check. Note C. So I1 plus I4 equals I2. Okay. Well, again, do it according to your designation. You don't have to copy mine. Do it according to your designation, and the answer should still be consistent. Okay, let's jump into any question about this, by the way. There's no question. We're going to jump into doing another problem. I'm going to solve as many problems as I can. Say problem. Okay, let's see 1 over omega is 2. So in this case, let's go ahead and calculate. active and reactive power in this impedance R2 and C, and then contribution of power by each source in R2 and C. Contribution of power by each source in R2 and C. All right. So since circuit is given in time domain, the first thing that we do is what? Convert into phasor domain. Convert into phasor domain. So this source is going to become Vs1 function of j omega 2 angle 2 volt, not 2 volt, sorry, 2 angle 0 volt. This source is going to become Is2 function of j omega 2 angle negative 20 degrees milliampere. And of course, we will calculate what is the reactance of XL1, which simply will be 2 times 2, 4. So that's going to be J4 ohms. XL2 will be 4 times 2, 8, J8 ohms. And then XC is going to be 1 divided by J omega C. So 2 times C, 0.2, 1 over 0.2 is what? 5, right? 5. So negative J5. Let's go ahead and plug these values in my MATLAB. So Vs1 is 2 and omega is 2, L1 is 2, R1 is 10, R2 is 20, C is 0.1, L2 is 4, and R3 is 5, and Is2 is 2 angle negative 20. So polar to rectangular pole, rec 2 milliampere to exponent negative 3 angle negative 20 degrees. Yes, Is2, Is2. And my XL1 is I times omega times L1. XL2 is I times omega times L2. XC is 1 divided by I times omega times C. Okay. All right, guys. So to calculate active and reactive power in the resistance in the capacitor and the common branch, what do you suggest? What should we do? Okay, we can perform nodal analysis, or we can perform mesh analysis, because in this case, we already know the current in the mesh on the right hand side. So whether we apply nodal analysis or we apply mesh analysis, we have only one equation. Doesn't really matter. So we can apply nodal if you want. Let's call this node A. All right. What will be the KCL equation at node A? Yes. I1 plus IS2 is equal to, right? Okay. And I1 is VS1 minus VA over R1 plus XL1. I'm just gonna call this Z1. I'm gonna call this Z2, and I'm gonna call this Z3. So in my program, I'm gonna do that first. Z1 is R1 plus XL1, and Z2 is R2 plus XC, and Z3 is R3 plus XL2. So Z1 and Z2 and Z3. So I1 is VS1 minus VA over Z1. IS2 we already know. And I2 is, this is I2. I2 is VA over Z2. So let's go ahead and figure out what is VA. VA is equal to, take this VA on the other side, it's going to become plus VA over Z1. And on the left hand side, we will be left with VS1 over Z1 plus IS2. And on the right hand side, we will have VA over Z1 and VA over Z2. So the common factor is going to be VA. And if we divide it, then it's going to be 1 over Z1 plus 1 over Z2. So VA is equal to VS1 over Z1 plus IS2 divided by 1 over Z1 plus 1 over Z2. 1.35 minus J 0.29. 1.35 minus J 0. Correct? Anyone else? Uh-huh. Pole rec? No, my pole rec function right here, pole rec. I'm calling it, yeah. That's my function. So I take R and I take theta. R is in, of course, magnitude. Theta is in degrees. And then I'm using pole to card function built in and converting theta into radians first, and then R and whatever my components are, I'm just adding them together. Z is equal to X plus R. Those are my functions. No, those are my functions. Because if I don't do that, then it is going to give you X separately and Y separately. Pole to rect function or pole to card function in MATLAB, it gives you the real part and imaginary part. They're separate, but I want to make them a complex number, right? So that's what I did in my program. I just did X plus JY. And that's the same function that you used in software class, actually, with the problem, that example that I showed you in the, not the example, there was an exercise that I asked you to do, or example, one of the things. Anyway, so VA is coming out to be this. All right, since we know VA now, what was our goal? Our goal is to find I2 to calculate the active and reactive power here. So let's calculate I2, which will be VA over Z2. All right, so that's giving me 67.3 plus J 2.26 milliampere. So now I can calculate. Again, since we are calculating active and reactive power, we can just calculate the complex power. Real part will be active, imaginary part will be reactive. So the complex power of Z2 is VA times the conjugate of I2. And it is coming out to be 0.09 minus J 0.02, or we can write this down in terms of milliwatt, and millivolt ampere reactive is 90.7 minus J 22.6 millivolt ampere, which means that the active power supplied to the resistive part of Z2 is 90.7 milliwatt, and the reactive power associated with that impedance is negative 22.6 millivolt ampere reactive. And again, you have the capacitor, so we expect that the power, reactive power, is negative reactive power. So it is always wise to calculate complex power if you have the voltage and current, because complex power gives you both active and reactive. So instead of calculating them separately, V times I times cosine theta minus phi for active, and V times I times. Oh, we forgot one thing. Voltages are in peak, so we did not convert that into RMS. So we have to go ahead and do that. These voltages are in peak. So every quantity here, all the current and everything, they are in peak. So I'm going to go ahead and do that here. VA over square root of 2, or VA over square root of 2 and I2 conjugate over square root of 2. So everything is going to be divided by 2. So that's going to be divided by 2. And this is going to be divided by 2. So let's calculate that. $45.3 milliwatt and negative 11.3 millivolt ampere reactive. So this is the total active power consumed in that resistance, total reactive power associated with the capacitance. The second part is calling for you to calculate what is the contribution of the total active power in R2 by this source and this source, and likewise total reactive power in C by VS1 and by IS2. So if a question like this is given to you, what is your approach? What you're looking for? Hold on. What you're looking for? How do you do that? What do you apply? Yeah, the second question is contribution of power by each source. If a question like this is given to you, what exactly you're looking for? What is your approach in order to find what is the power delivered by VS1 to R2 and C, and what is the power delivered by IS2? We calculated total power right now. So out of that total power, what is the contribution of VS1? What is the contribution of IS2? How do you do that? Mike, what do we need to do? All right. And what do you call that? Okay. Superposition. Yes, superposition. That was a problem given in exam 1 as well. And nobody did it correct. Well, no, some people did it correctly. So you have to apply superposition if you're finding the contribution of individual sources, right? Again, you guys forgot about that. That's not good. That was a problem given in exam number 1 for DC circuits. So we're going to apply superposition, keep one source at a time in the circuit, and then find only the power due to that source. So let's go ahead and do VS1 first. Keeping VS1 in the circuit. Let's go ahead and redraw the circuit real quick. All right, once we eliminate IS2, what's going to happen? Yes, Mike? Elimination of IS2 means what? Okay, so we're going to open that. That means what's going to happen to the circuit? Which inductor is there? L2 and R3 will be gone, so you will have only a single loop. So so your circuit is reduced to VS1, R1, L1, R2, and C. VS1, R1, XL1, R2, X. And we can easily find the power in R2 and XC. Let's find the current first. Let's call this current due to IS1. Or let's call this I. Give me 1 second. Yes, go ahead. Yes. Let me go back. What is your question, Rodley? For circuit, this means why the current in this is IS2 or yeah. You can label it anything that you want. It's just a label. Yeah. No, it's a label. You can call it IS1 if you want. That's fine. This is a current coming out of IS1, so you can call it IS1. We don't know that current. We are trying to find that current value. We don't know that, but you can call it whatever you want. I call it I1 because it's going through R1 and L1, so I just call it I1, right? Because this is just going through R1 and L1, and then it's going to divide basically because it's going to come to a node, and then it's going to divide between the two impedances or two branches. Okay, so going back to the circuit, let's calculate I2. I'm going to call it I2 prime because of VS1. I2 prime, of course, is equal to VS1. And remember, this was Z1 and this is Z2. So VS1, Z1 plus Z2. I2 prime is equal to Vs1 divided by Z1 plus Z2. Okay, that's 66.59. 66.59 plus J 2.21 milliampere. And that is going to give us the power in R2 and XC. Let's calculate that, which implies power in R2. Let's call it PR2 prime from the first source, magnitude of I2 prime divided by the square root of 2 square times R2, and QC prime is magnitude of I2 prime over square root of 2 square times magnitude of. So we are using I square R and I square X here because we know the current passing through R2 and C. And once again, use the correct variables and the correct values. Yes.
That's good.
RMS, because we are using peak values of current. Yeah. Input is given as peak, so all the current and voltages are peak, basically. RMS. RMS. So let's go ahead and calculate that. PR2 prime is equal to absolute value of I2 prime divided by, I'm just going to divide it by 2. So absolute value of I2 prime square of that times R2 divided by 2. So 44.39 milliwatt. Oh, wrong. Yeah. 44.39 milliwatt, and QC prime. QC prime is absolute of I2 prime square times absolute value of XC divided by 2, and that's, and remember this is negative because we are calculating for the capacitor. So you have to put a negative sign, otherwise it's going to just going to give you a positive value. So negative 11.0 millivolt and sorry. Yeah, if you use the complex, then you will not, yeah, you will not forget this negative sign for sure. Yeah. So if you don't want to make that mistake, then calculate the voltage across this first, and then use the regular complex formula basically. Now, so this is a contribution by the first source. Let's look at the contribution by the second source as well. Although if you know the total power, then you can just subtract it, and rest of the power is going to be coming from the other source. But we're going to go ahead and calculate it, and then see if we add the two, it's going to come out to be this value. So let's go ahead and use this. And to use this, we are going to shut down VS1. So when we're going to shut down or deactivate VS1, what is going to happen? No. Okay. All right. So we're going to short the source. So R1 and L1 resistor in the circuit, since we are shorting the source, and those will appear in parallel to R2 and C. So first we're going to redraw the circuit just so that we don't make any mistake, and then go from there. Now, to calculate the contribution by IS2, deactivate VS1, short. So the circuit is going to be short. So that's going to be your circuit. IS2, XL2, R3, R2, XC, R1, XL1, and of course this is node A that we assigned in our original circuit. All right. So what we're looking for to calculate the power contribution in R2 and XC. What do we need to know in order to calculate those two quantities? Current, and how are we going to find it? We can use current division in this and find the current passing through the impedance Z2. So remember this again, this is our impedance Z1. This is Z2, and this is Z3. So use current division and find what is the current passing through. We call this current I2 so prime, so I'm going to call this current I2 double prime because of source IS2. To calculate the power in Z2, we need to know I2 double prime, for which we can use current division. Let's do the current division. I2 double prime is, all right, who is going to tell me if I'm writing current division, then what will be my equation? Hold on, hold on. Yes. Yes. Yes, Mike. Okay. Excellent. Very good. Excellent. So our equation is simply total current times whichever impedance are connected in parallel through which the current is being divided, total current is being divided. In this case, we have two impedances connected in parallel, which are Z2 and Z1. The parallel combination of Z2 and Z1, that is the equivalent, Z equivalent, divided by the impedance through which we are trying to figure out the current, which is Z2. So I2 double prime is equal to IS times the parallel combination of Z1 and Z2 divided by Z2. Let's see what is defined. IS is undefined. Let me see why IS is undefined. IS2, that's IS2, not IS. Okay. IS2. So let's change the designation. This is IS2, so this is IS2. So I am getting, let's see what I'm getting. I'm getting 0.71 plus 0.04 plus J 0.04 milliamp, 0.046 or 0.046 and 0.716 milliampere. See if you're getting the same result. Got it? Okay. And since now we know the current, then we can use the same what we used here to calculate the contribution of power from IS2 into R2 and XC. So now calculate that. Therefore, power in R2, I'm going to call it PR2 double prime, is equal to I2 double prime magnitude divided by square root of 2 square times R2 QC double prime I2 double prime magnitude over square root of 2 square times XC, and don't forget the negative sign. So I2, what is that? D prime, right? Oh, mistake over here. Call it ISD prime, same thing. Let me correct it just to make sure that I'm consistent. Let me call this I2 D prime. I2 double prime IS2 times RP. Okay. All right. So now I can easily write down PR2 prime is I2 D prime. Absolute value is squared divided by times R2 over 2. So this is D prime. That's 5.14 microwatt. And QCD prime, double prime, is absolute of I2 double prime square times this 1.28 microvolt ampere reactive. So negative 1.2875 micro. So PR2 is equal to P. So if I add both of them together, I'm going to come out to be 44.4 milliwatt, so 44.39 milliwatt. And if I add both of these two together, 11.1 milliwatt. And we have, yeah, negative 11.0 something millivolt ampere react. So these will be our individual values, of course. Contribution from source 2, contribution from source 1, and when you sum up those things, you're going to get the total power in the resistive part and in the reactive part. I should put down here. This is PR2 and QC, because R2 and XC are part of Z2. And those are the values that I'm getting. When I added the two powers together, then I'm getting 44.4 milliwatt as a total power in resistor 2 and negative 11.1 millivolt ampere reactive. Yes, let's round up. You have to round it up. So the first values that I put down was a big figure. So, yeah. You will never get exactly the same value. It is always going to be round off at minor errors. Yeah. So we're going to take a break. If you have any question, please feel free to ask. Let's pause recording. Okay, so XC is 1.5 negative and XL is 2.8. All right. And, oh, it's not. XL is 2.8. All right, once again, since it was not recorded, so once again, just to explain, if somebody is watching this video, in order to calculate the power, active power, again, active power is only consumed in the resistive part of the circuit, which is also the average power and the real power. And that power is going to be consumed in R1 and R2 only. But again, you should solve power for in each component, and your average power in XC and XL should come out to be 0. I'm going to just calculate the active or average power in R1 and R2. And for that, we need the two currents passing through the two resistors, which are IS and I2. IS, of course, we will combine. We'll do the parallel combination of XC and R2 plus XL and find total current IS using Ohm's law. And then we apply the current division to find I2. And to find the total power supplied by the source is simply Vs times, or total power, active power will be magnitude of Vs times magnitude of current Is times power factor of the source or power factor, which is angle of Vs minus angle of Is, cosine of that. So that's what we are doing right now. All right, I entered all the values in my MATLAB. So let's go ahead and calculate the impedance Z, which is parallel combination of X of C and R2 plus XL. And that came out to be 0.6314, 0.631 minus J 1.77 minus J 1.77 ohm. So this is the parallel combination of this. If you're getting a different result, then let me know. Okay, so now we're gonna calculate Is is equal to Vs over, what was that, R1, right? R1 plus Z, R1 plus Z, simply Ohm's law. So Is is equal to Vs divided by R1 plus Z. 51.32, 51.32 plus J 62.02, 62 M. So we can calculate first the total active power, total average power supplied by the source. P source is magnitude of V source, magnitude of source current. And again, in the problem, it is not mentioned that this quantity is peak or it is RMS. So we can assume it to be peak and then calculate based on that. So let's assume this quantity is peak. That means we're gonna have Vs over square root of 2, RMS value of that, RMS value of that, and then cosine of magnitude of Vs, phase of Vs minus phase of Is. All right, so absolute value of Vs times absolute value of Is times cosine of what? 5,286.5 or 5.286, 5.2865 kilowatt. Let me know if you're getting the same result or different. So that's the second part. We calculated it first since we already had the Is value. Now we're going to calculate the individual powers consumed in R1 and R2. PR1 is, again, since we know the value of Is, and Is is passing through R1, Is is passing through R1, so we can calculate that first. PR1 is magnitude of Is divided by square root of 2 square times R. That's the average power in R1, active power in R1 is the same thing. PR1 is equal to absolute of I1 square times R1 divided by 2. IS, not I1. IS 3240 3.2404 kilowatt. And for PR2, we need to calculate the value of current passing through, value of current passing through here, I2, and that we can use the current division to calculate PR2. We need I2. I2 is equal to total current times the equivalent impedance that we had calculated already, which is Z, equivalent between XC and R2 and XL. So Z over R2 plus XL. Z divided by R2 plus XL, because we are trying to find the current passing through the series combination of R2 and XL. So I2 is equal to IS times Z divided by R2 plus XL. 16.746 minus J 32.919. Therefore, PR2 is magnitude of I2 over square root of 2 square times R2. Hmm. 2400 to 2046.1 or 2.0461 kilowatt. And to confirm, what is the total power? Total average power, PR1 plus PR1 plus PR2. Let's calculate that. P is equal to PR1 plus PR2, and that's 5286.5, 5.286 kilowatt. And let's see if that's the total power we calculated, which is exactly the same. This is equal to total power of source. So it's checked out. Which means again, which means what? That in the inductor and in the capacitor, there will be no average or active power that is going to be consumed, as we have discussed, because average or active power is only associated with the resistive part of the circuit or resistors of the circuit. If this would not be the same as the total active power of the source, then you know that there is some calculation issues somewhere. All right, guys, question. because of course you don't, for resistor you can use this formula I square R, but for the power from the source you always have to use V times I. And in this case, since it's the AC source, so the source is providing both active power or average power and reactive power. So then to calculate the active power, you want magnitude of V RMS, magnitude of I RMS times cosine of the phase of V minus phase of the current, which is the power factor. And to calculate the reactive power supplied by the source, you have magnitude of current, magnitude of voltage, RMS value, magnitude of current, RMS value, sine of phase of voltage minus phase of current. Those are the standard formulas. As I, repeating over and over again, make sure you have all those power formulas written somewhere in front of you, or create a program with, and then just plug in the values of voltage and current, and then the program is going to spell out all the powers. Because again, those are standard formulas, they're not changing. If you have memorized them, very good, but it's convenient to have them in a program, a small program, so you don't have to punch in the numbers. All you need to do is to put the voltage, put the current, and then it is going to give you the calculation of all the power value, power factor, and all those things. So do that, please, so that you don't waste time in the simple calculation. Again, your job is not the calculation. I'm not looking for the calculation, and that's an issue. A lot of you, most of you, maybe except one or two, you spend a lot of time in calculations. Calculations, you see that, right? Calculations are piece of cake. It's like less than a second you can do what some of you can take like 10 minutes to do the same thing and still make mistake. I'm not looking for calculations. I'm looking for your understanding and how you're going to solve the circuit, analyze the circuit, to take the right approach to solve it. And that's why I don't, I put everything in terms of algebra. I don't put down numbers. If you're putting down numbers, you're gonna make mistakes. You're gonna take longer. You're gonna be confused. What is, if you have 200 ohms, for example, you put this 100 ohm, and then I was like, and when I'm reading your solution, I was like, which 100 ohm you're using? Then I have to go back to your circuit and check. So if you have R1 and R2, I know instantaneously, oh, you're putting for R1, you're putting for R2, although both may be 100 ohms, right? So it's always wise to use variable. Even if they're not given to you in the circuit, assign your own variable, that R1 is this and this. I try to give you, but if I'm copying a circuit from, let's say, textbook and giving you for a quiz or exam, many times it does not have the variables, it has just have numbers. But I try to just assign variable. Yes. Yeah. It's gonna be same phase in R1 and same phase in R2 because it's a resistive component. Cosine is going to be 0. Sine is going to be 1, and cosine of 0 is going to be 1, and sine of 0 is going to be 0. So no reactive power. And opposite is going to be in XC and XL. Current and phase are going to be 90 degrees apart. So cosine of 90 is going to be 0, no active power, and sine of 90 is 1, pure reactive power. So there will be reactive power supplied by the source, which is going into XC and XL, but active power is only consumed in R1 and R2, and that's what we saw, that the active power of the source is the same as the total combination of the active power in R1, R2, which average power is the same as active power. If the problem also asks you calculate the reactive power in the passive components, and then prove that the source is supplying the total reactive power, then you're going to concentrate on XC and XL, calculate the reactive power, and then calculate the reactive power of Vs and show that that's the reactive power. We can do that real quick. So let's do that since we have a couple of minutes, and it's going to take a couple of minutes to do that. Total reactive power supplied by the source. Qs is magnitude of Vs, magnitude of Is, square root of 2, square root of 2, sine of angle of Vs minus angle of Is. So this power is going to come out to be, let's calculate that. So Qs is equal to absolute value of Vs times absolute value of Is sine of angle of Vs minus angle of Is divided by 2. Parse error, let's see. Oh, multiply. Forgot multiplication. Angle of Vs minus angle of Is. So that's going to be negative 5747. So it's a capacitive circuit basically. Source is looking at the load as a total capacitive load. So this is negative 5.7472 kilovolt ampere reactive. So this is the total reactive power. Now we will see if the combination of the two powers, reactive power that is dissipated in capacitor and dissipated in inductor, is going to come out to be the same as supplied by the source, in this case the total capacitive power. So how are we going to calculate the one? This is easy. How are we going to calculate this in the Excel? Yes. Anyone? No, try to multiply by Excel. I2 square. I2 square times magnitude of Excel. Come on, guys. You've been doing it over and over again. And when I ask you a question, you guys just, it's like, reactive power in XL, Q, let's call it QL, is equal to magnitude of I2 divided by square root of 2 square times magnitude of XL. QL is equal to absolute value of I2 square times absolute value of XL divided by 2. 1909.7, 1000, so 1.9097 kilovolt ampere reactive. Remember, Q for inductor is positive, and now reactive power in XC. Okay, now who is going to tell me again? Let's go back to the circuit. Who's going to tell me how to find the reactive power in XC? Say it again. Okay, so find the current passing through XC, which is IS minus I2, and then apply the same formula. Excellent. We can show that this is IC, IC. QC is equal to, again, use a negative sign. IC over square root of 2, magnitude of IC over square root of 2. Let me move these parentheses from here. Square times magnitude of X minus IC is IS minus I2 divided by square root of 2 square. So IC is IS minus I2, and then I'm going to write down QC is equal to negative absolute value of IC square times absolute value of XC divided by negative 7656.9, negative 7.65669 kilovolt ampere reactive. So now do the check. Total Q total is equal to QL plus QC, which is equal to Q total is equal to QL plus QC, negative 5,747,742 kilovolt ampere reactive. Let's go and see if it's the same as the source, negative 5.7472 kilovolt ampere reactive. So this is equal to Q source. So we checked it. So as you can see, source average or active power is going into only the resistive components, and source reactive power is going only in the reactive components. And that concludes our class today. If you have any question, I'm here. You can ask me anything there. So Wednesday, what do we have first? Quiz. Quiz is going to be comprised of both what we are doing here, basically, because what we are doing here, it requires you to do first AC analysis, calculate voltage, calculate current. So that's chapter number 10. And then you are calculating power, right? And power requires you to have those values, current, voltage, or whatever. So it's going to be a combination of chapter 10 and chapter 11. So homework is due as well. 5 problems that I assign you, that is due on Wednesday. Quiz is going to be there, and then after that we're going to do the lab. Now again, lab is very easy, but you must do the pre-lab so you know what you're expecting, because lab is as easy as just connect the components, turn the oscilloscope on, look at the waveform, measure it, and that's it. You're done. So the lab is extremely simple, but do the pre-lab. Make sure, do not forget the pre-lab. Requires you to do both theoretical calculation as well as piece-by simulation. And then the following, I think the following Monday is the exam from power, AC power, or AC 10, chapter 10 and chapter 11. All right, guys, I'll see you guys on Wednesday.